your code runs in a smooth way, in a better way. For example, if your code crashes for some reason, or if your sensor stops working, you don't need to kill your entire application in order to restart it. You can use just a couple of commands and you can handle all these errors with the services. It's improved way of writing applications for ROS2. Anyone has questions? No? Okay. So today we'll try to understand what are ROS2 lifecycle nodes, and we'll explain the purpose of these nodes and what makes them different from normal ROS1 nodes or normal ROS nodes that you can also write in ROS2. So normally with ROS, you would write your nodes in a way that you would have a class, and inside of your class, you would have your constructor. Inside of your constructor, you can have your publishers, you can have your subscribers, services, clients, and also actions. And all this information would be described and in some way defined once you start your application, your custom ROS package, whatever you're trying to write. This has benefits and it also has some downsides. When you, for example, want to write a very simple application to acquire sensor data, and your sensor is publishing data in a certain way, for example, according to some specific ROS coordinate frame. You can have NED or EUW, for example, according to the information that is provided from your IMU. And ROS2 node life cycles allows you to define the way that your node works and your parameters work without having to kill the application. So for example, if you are starting your node for the IMU and you want to acquire the data at a specific frame rate, for example, let's say 100 Hertz from the IMU, and for some reason then you need to update the way that your sensor data is being acquired, you can do that without having to restart the entire application and without having to restart your node and your system in general. So ROS2 introduces the concept of lifecycle nodes, also called managed nodes, and this system allows you to ensure that all the requirements for your application to run correctly have been started. Okay, so if you need, for example, to have some connection with your sensors, with your hardware, it allows you to do the proper configuration, and the nodes also can be restarted on the fly without having to restart the entire application. ROS node life cycles also follow the state machine that you can see here on the right, and I will explain all of these states and what they mean in the next slides. But we can see right from here that we have a couple of transition states that are represented here at yellow, and a couple of states that are represented at blue. And these one are not transition states, these are active states of your node. So the lifecycle nodes, as I was explaining, have the different states. The ones that are transition ones are represented at yellow, and the primary states are represented at blue. And the primary states, the ones that are represented at blue, are supposed to be states in your node can be in a stable way. They are not called transition. And for example, if your node, when you start your node is in an unconfigured state, and this is a steady state of your ROS application, which means that if you don't do anything, if you don't provide any kind of input, your node will continue in this state. So it will be unconfigured and just waiting for some kind of configuration, some kind of input from the user or from a service application that you can have running, managing your lifecycle nodes. And on the other hand, the transition states that are only temporary, and they are represented at yellow, and they are attached to some kind of transition. For example, if you are configuring your node because your node starts in unconfigured state and then you are doing some kind of configuration, that configuration is doing on these transition states, and then these transition states can have some kind of return that can be successful or it can be a failure. And based on this successful or failure, your node will change the state. So, for example, here you can have the configuring state, and if you have some kind of problem, the node will go back to unconfigured state, and you can do the reconfiguration of your node. And as I was explaining, the result of these transition nodes are used as a return in order to change between the different nodes that you have. We have here the primary state unconfigured, and the unconfigured state is the state in which every single node starts, every single live node starts. So it means that your node is simply running, it's alive, but it's not receiving any information from your publishers, not information from your subscribers. And even if you try to send some kind of data to your node, nothing will happen because you don't have your publishers active or your subscribers services on actions. The node is just idling in this state, and it's waiting for some kind of input from the user or from the service client that will provide this information. The node can transition from the unconfigured state, that is the initial state in which the node starts, using the configured transition state. And after this, it will be in the state inactive. So during the configuration, you declare all the information that is related to your node. Everything that you need in order for your node to work properly needs to be defined at this stage. It can be, for example, the parameters, any kind of parameters that you are using. For example, if you are defining the maximum velocity for a robot, the maximum angular velocity, the number of publishers, number of subscribers subscribing, for example, to the GPS information or to the IMU information, so on and so forth. Wait. The inactive state, that is the state that you have after having a successful configuration of your node, it's still not receiving any kind of information. It just has the publishers and the subscribers services and actions parameters also available in ROS. But if you send any kind of information to this node, nothing will happen. So the node is properly declared, it's running, but it's in a idle state, and no kind of processing of information is currently happening at this stage. The main purpose of this inactive state is for you to be able to reconfigure any kind of parameter on the flight. So you don't need to kill your node in order to change, for example, the sensor that you are acquiring data from. You don't need to kill your node to restart the frame rate. You don't need to kill your node to do any kind of reconfiguration of the node itself. And as I mentioned, in this state, the node will not receive any kind of execution. Even if you send data to the publishers, nothing will be received from the subscribers. So it's in a idling state, and nothing will be read from the information that is sent to the node. The node will not be processing any kind of data. After the inactive state, we can activate our node using the active transition state. And the inactive state has three possible options. So the node can transition to the shutting down if, for example, it receives the information to shut down because it's not necessary to run the node anymore. It can also transition to the unconfigured state if you want to clear the publisher, subscribers, or actions or services that you have currently running in your node, and you want to declare something different. And it can also transition to the active state, that is the state that we care about at the moment, and it is this one. In the active state, this is the main state of our ROS2 application, is where the information will be processed where some kind of meaningful output will be created from the information that you acquire from your subscribers and from your publishers. And this is where the node processes the any kind of information. It handles the service requests, the timers, the callbacks, and everything is done in this active state. And if any error cannot be handled during the active state, the node will shut down. It is represented here in the finite state machine. And from the active state, the node can transition again to inactive, like it's represented here. And if some kind of error occurs that it's not possible to handle the error, the node will transition to the error processing state. From the error processing state, if we can handle the error, we'll be transitioning to the unconfigured state, where we can do the configuration of your node again, and we can restart everything that needs to be restarted in terms of, for example, the acquisition of the data from the sensors or the connections, the serial connection to the sensors that we have. This allows us to restart our application, and without having to kill the node and without having to kill the entire software stack that is running in the robot. So it's more modular, more reactive to whatever errors we might occur, and it allows us to handle the entire system in a more friendly way and to handle errors in a more the way that is more friendly in terms of the development and for the entire system in general, because you don't want to have an error and you just don't want your system to completely fall apart and stop working. So then we have here the last one of the steady states that is called the finalized state. And this one is the state that the node ends every time you are killing your application. So the last state is always a finalized state. And the purpose of this state is only for debugging. If you have to do some kind of digging and understand what happened to your node and why it died or why it didn't work properly, you can use the finalized state in order to do this kind of inference and to understand what happened and what went wrong. As you can see here from the finite state machine, the finalized state only has one option, that is to destroy the node and to exit the program. Okay, we covered all the steady states, and now we'll be talking about the transition states. And these are the states that are actually doing the work between the steady states and what will allow us to configure our code and our application in order to have our node working properly. So we have the configuring, activating, deactivating, cleaning up, shutting down, and error processing. As you can understand, the configuring node will allow us to define everything that is related to the configuration of our node. So this is a callback in our ROS2 application that will be called once we want to transition between the unconfigured state and the inactive state. And in this callback that you defined the publishers, subscribers, everything that is defined for your ROS application to be able to run, such as the services and also actions, parameters that you might have from your launch file, so on and so forth. Then you have the activating state, and this is the state that actually turns on your the parameters and the subscribers and publishers that you defined in the unconfigured state. Okay. So as I was explaining, the transition state has a callback. The configuring state has a callback that will be called when we want to configure our node, and this can have external trigger from a service client that will start the node, or you can also, for example, do it from the command line. It's also possible to do it with your ROS application. um, the callback that allow us to do this configuration is called the unconfigured callback, and upon success of this callback, we'll transition to the inactive state, and if we have some failure, it will go back to the unconfigured state. If the unconfigured transition raises some kind of error that is not possible to be handled, we are going back to the error processing state. And after that, if we are able to handle the error, our code will go back to the unconfigured state. Otherwise, it will go to the finalized state. Then we have the cleaning up transition that is shown here. And this transition state will be called when we want to clear our publishers and subscribers services and actions that were previously declared on configured state. And this will make our node without any kind of predefined or without any kind of ROS interface communication. So you won't have anything running at this moment. And of course, if the cleaning up is successful, it transitions to the unconfigured state. The onCleanup callback raises the result if some raises an error, if something goes wrong, and it also transitions to the error processing state. Then we have the activating callback. This is the callback that actually enables our services and our the communication between our raw system to run properly between our nodes. And upon successful, we transition to the active state. And the name of the callback is onActive. And if this callback is not successful, we go back to the inactive state, like it is represented here. So on success, we transition to active. And if something is wrong, we transition to the inactive state. We also have the deactivating state. If for some reason you need to stop your node and you don't need the processing to be running anymore, this can be used if you want to save resources, if you are doing some kind of, for example, AI application that is using the CPU, or you want to reduce the processing power or the power consumption of your machine or the CPU usage, you can use this state in order to stop your node from running. And the name of the callback is on the active, like I mentioned before. And upon a successful state or transition, we are going to the inactive state again. And if some error is raised, we go to the error processing. Then we have the on shutdown callback, and this method is expected to clean up any kind of data that or interface that is still running within our raw system. So it is supposed to clean up the node and to clean up our application in order to have gracefully cleaning up of the node and shutting down of the node. If the shutdown callback is successful, it will also transition to the finalized state. And if, as all the other transitions, if there is some kind of error, something is thrown, we go to the error processing callback. And finally, the last transition state, that is the error processing. And in this state, if we have some kind of error, this callback will be called, and this is where we are supposed to handle the problems of our code. And if something is wrong, it needs to be handled in this state. If we are able to solve the problem, for example, imagine that you have some kind of interface to your sensors and you need to restart the serial port in order to be able to communicate with your LiDAR or with your IMU or with your camera, so on and so forth. If you are able to do it, you go back to the unconfigured state. Otherwise, your node is terminated and it transitions to the finalized state. Okay, and the final one is the destroy and create. These are represented here and here. And the destroy transition will simply cause the delocation of the node. and this basically will call the structure of our class, and this transition is always successful, and your node ends and terminates the processing of whatever is running. The creation transition will simply create the node, it will instantiate the node, but nothing will run because the node will be in the unconfigured state and it will be idling. Okay, now I'm going to demonstrate how this node lifecycle works, and I will maybe do it live. Mm, already have here the result of what is expected to have. So we are running three, oops, we are running three different nodes. First, we are running the lifecycle talker, and this is simply a lifecycle node that will be publishing information to the ROS system. Then we have the lifecycle listener that is supposed to listen to whatever information is being published. And we have our ROS2 lifecycle service client that is responsible for doing the transitions between the different states of the lifecycle node. So it will cause a transition from the unconfigured state to inactive, from inactive to active, and from active to shutdown. So here I have a simple turtle sim that is a raw simulation tool, and we'll be able to control this turtle sim using the different commands from the lifecycle node. So, okay. So what I first did was to just launch the turtle sim with the turtlebot control, and my launch file that is represented here at the top is also launching the controller that I wrote for the lifecycle nodes with ROS in order to demonstrate how everything works. Here we have the command that I used in order to be able to see what were the possible transitions from our nodes. So our node was first started and it's in configured state. And from the unconfigured state, we have two options. First, we have the option of configuring our node. And secondly, we have the option of immediately shutting down our node, like it was represented in the finite state machine here. So as you can see, our node started and it has two transition possibilities. From the unconfigured, we can go to shutdown, like is represented here. And we can also go to the configuring transition state that is represented here. We can get this information using the ROS command line lifecycle list, and then you need to pass the name of your node. And we can also get the current state of our node by using the lifecycle get that will get us the current state of our node. And as it is expected, the first state is unconfigured because it's the first state of our finite state machine. And then what I did, I decided to run configured node, and from configured, it transitioned to the inactive state. And after transition from the inactive state, I activated the node, and we get here the result of the transition successful or transition not successful. If the transition was not successful, it would go back to the unconfigured state or to the inactive state. So now I will run the commands again, and I will show it running with our turtlebot controller. So first we'll see the current possibilities that we have. We have two transitions possible that are the configuring and the shutting down. And we want to do the configuring of our node. Yes. If I'm able to find my notes. Okay. So at the moment, our node is in the configured state, and in the inactive state because the node was properly configured and the transition was successful. And if I run the ROS2 lifecycle list again and with the name of our node, we should get the different transitions that are currently available. So we see that we have the cleanup, active, and shutdown transitions, and we want our turtle to move. So we will request the transition to be active at the moment. So we want to run the active transition, and that's what we are going to do now. And the turtle should move. And this is exactly what happened. So we are sending the information from our publishers to our subscribers, and the turtle sim started moving because the nodes were properly activated and the system is currently running and receiving the information. So now we can get also the other transitions that we have from the active state. And the transitions that we have from the active state are the shutting down and to the deactivate transition. And if we run the deactivate transition, the node will stop and it will go to the inactive state again because nothing will be published. And if we run the shutdown, the node will simply it will be simply killed and the turtle will stop running. Here, I just have the information on how to get the different information from our ROS2 node lifecycle regarding getting the current state of the node that can be used with ROS2 lifecycle get. We also can get the list of possible transitions that are acquired with the ROS2 lifecycle list. We can use the ROS2 lifecycle set in order to set the different transitions that we want between the different states of our nodes. In this case, is ROS2 lifecycle set. And I just have an example that would be the lifecycle talker, and we are transitioned to successful. And from successful, we transition to the inactive state. And after the inactive state, we will finally transition to the active state and the node will start running like it was demonstrated. And with this, I will end my presentation. If anyone has questions, please just let me know. You can get some information from the ROS life cycles. And also, if you want to run the code that I just demonstrated here, you're also free to go to my GitHub page and you can get all this information. And to be able to just do the demo like I did here, the source code is available. So please just feel free. First question is from here.
Sure. Hello.
Hi.
Thank you. Thank you very much for your presentation. I'm actually totally new to ROS. So to get some intuition about these nodes, and so would you give some examples what would be in the real world, like a talker node, listener talker, and so listener node, and so on?
Sure.
Thank you.
So for anyone that is new to ROS, a listener and a talker and a publisher and subscriber are basically ways of transmitting information between your nodes. So in software applications, we want to have things modular in order for you to have one component working in with a specific piece of hardware. For example, a driver from your LiDAR. The driver from your LiDAR is only responsible to acquire data from your LiDAR and publishing to your ROS system. What happens with that data is not responsibility of the driver. So your driver acquires the data, publishes to the ROS system, and you have some kind of subscriber that will get that information from the data that was published and will process this data in order to create something meaningful. Because what you get from the LiDAR is just raw data, and you want to transform this raw data into something that would be useful for your system to do some kind of decision making. If you have, for example, a car ahead of you, your LiDAR will not tell you that information. You need to have some kind of processing. So we tend to have things in a modular way so that your nodes can also run independently in the independent way. And if some part of your system die, not everything will die. So I don't know if this answered your question, but you have the publishers and you have the subscribers, and publishers are responsible to send the data from whatever they are acquiring from to your subscribers. And this is how the information flows within ROS. You can also have services and actions, and this is another way of communicating using the ROS framework. Anyone has questions? Yeah.
No, thank you. So two questions really. The first one is how, in your opinion or experience, how well does the error handling work in these life cycle nodes? So how does it catch really every error that happens in the active state and transitions to the to this error state? I don't remember the name.
The error processing state.
Okay.
Yes. So far, in my opinion, it works quite well. The information that if you have some kind of error independently on the state that you are in, everything is handled by the error processing. But this happens from your steady states, like I was showing here in the final state machine. So as you can see here, only your transition states when you are doing something, some kind of activation of your node or deactivation of your node, or the cleaning up or shutting down, only these states have the possibility of transitioning directly to the error processing state. And from my experience, it works quite well. And I don't have any kind of downsides in terms of the ROS node lifecycle. For example, I used it previously in order to speed up the launch of the nodes, reducing the CPU consumption in some applications that were a customer requirement, and the customer wanted the application to be faster, and I used this ROS2 node life cycles in order to achieve that. So when the robot was not needing any kind of in this case, it was a second navigation stack that was running. We will be able to shut down the second navigation stack, and we will be able to save a lot of processing power, and our entire software stack would run in a smoother way.
Okay. So my second question is, in your example and in most examples I have seen, the transitions are triggered by some outside source, some by hand or some lifecycle manager. And is it possible, and if it is, should it be done to sort of for the node to transition itself, if you know what I mean? So is it a good practice for a life cycle node to trigger its own transitions on some conditions?
I think that is heavily dependent on your robotic system and how you want to manage the nodes. And it's not a one solution fits all kind of scenarios. It depends on what you're trying to develop and what is your specific application and how critical some nodes are for your system. Because if you have some transitions that failed, probably in a critical application, you want your entire system to be on hold or to idle while you are restarting the node, and you don't want that to happen automatically. So I would say that is heavily dependent on your robotics application and on how important is the module that you use the life cycles on in order for the entire safety of your robot.
Okay, thank you very much.
You're welcome.
Thank you for your presentation. And I have a question. Let's assume we have ROS2 stack, and additionally we have several ROS1 nodes and have a ROS1 bridge.
Mhm.
And the question is it possible to map somehow this approach, a life cycle approach, I mean, to that nodes that behind the ROS1 bridge?
As far as I am concerned, there is no library that allows you to do the ROS to node life cycle for ROS1. This is something that was introduced with ROS2. And if you want to have some kind of application that respects the life cycle nodes, you'd have to have your own implementation with maybe some kind of actions and that would trigger the transition between states in ROS1. If I'm explaining, if
So the bridge doesn't support this
no,
approach. Okay,
no.
thank you.
As far as I know, it doesn't support this the ROS2 node life cycles.
So my question is, how would you distinguish between the, let's say if I had to code my own system, let's say a complex system, how would you distinguish if a node should be a lifecycle node or not? So should we code all nodes, in your opinion, as a lifecycle nodes, or should just use, for example, on demand? So use some of them as a regular nodes and some of them as lifecycle ones.
That is also heavily dependent on your application. If you are doing something for your prototyping, I don't think you need to code anything with lifecycle nodes. You can just have your application running. If you want to have proper error handling and proper management of your node, you should use the ROS2 node lifecycles, and it would give you more robust system in general and more also modular and something that you can integrate easily with anything that is running with ROS2. So, but if you are just doing some kind of prototyping, you just want some sensor working and published with ROS, you don't need ROS2 node life cycles.
So for production systems, you would say it's better to do all of the nodes in the lifecycle mode, or?
Yes, for sure.
For sure. Okay. Thank you.
Yeah, thank you for the presentation. Would it be possible to show some example C++ code of the lifecycle node?
Yes, for sure. Mm. Mm. So here you have the different callbacks that I was referring before. We have the unconfigured callback, on active, on deactive, on cleanup, and on shutdown callback. And this is the node that was running in order to make our turtlebot move. So we have here on our unconfigured callback the declaration of our publishers and also some of the parameters that we use for our turtlebot to move. In this case, we have the velocity linear and the velocity angular. And we also have the timer that will publish our messages periodically. And then we have the onActive callback that will activate our publisher in order for the information to be forwarded to the turtlebot controller, to the turtlebot simulator. This is the turtlebot controller, the node that I'm showing. We have the onDeactive transition that will deactivate the publisher, and we have the onCleanup transition to reset both the publisher and the timer. And this is the basic structure of our node. It inherits from the lifecycle node class. And we have our simple constructor that in this case is not doing anything. It's just telling us that the node has started, but the configuration of our node is done here. I don't know if you have any questions regarding this code exactly, or
So, like, if you could go one by one, like from each state, and describe.
So maybe it would help if I have the state machine near the code, if that's somehow possible. So first we have the onConfigure callback that is called from when our node transitions from the unconfigured state to the inactive state. And in our state machine, this is defined here on the right side. And here we have the onConfigure callback and what is running when we transition from the different states. And in this case, you can have the publisher declaration, the declaration of the parameters, both the linear and angular velocity, like I described previously, and also the timer that will run and it will publish the information at the desired frame rate. In this case, it's 20 hertz. And at 20 hertz, this message will be called, and the information from the velocity that we want to publish, it will be published. So here we are filling we are creating the message. Here we are filling the message with the parameters that we got from our unconfigured state, and then we are publishing the message. Again, this will only run once we activate our publisher. So even with our unconfigured callback running, nothing will be published because our publish is on this deactivated. So no information will be transmitted to the ROS system. Then we have the onActive callback, and in this onActive callback that is represented here on the right on our final state machine, we are simply activating our publisher. And after this, the information will be simply transmitted to the ROS system and our turtle will move. Then we also have the onDeactive callback, and if we call this callback, we are deactivating our publisher when we are transitioning back to the inactive state. And we also have the onCleanup and the onShutdown callbacks that the onCleanup we transition back to the unconfigured state, and we don't have any kind of declaration from our publishers or subscribers or timers. And on shutdown, we clear the entire system, everything that is running, also from the timers and the publishers, and we transition to the finalized state. And here on the bottom of our class, we are just defining our member variables. In this case, is the information that we are publishing, and the information that we got from our launch file. In this case, is the linear and the angular velocity, the declaration from the timer, and the declaration from the publisher that we are using to publish the information to the ROS system. All this is available on the GitHub page. I can share the presentation, and anyone can just check the code and maybe, I don't know, have some kind of template in order for developing your own lifecycle nodes. I think sometimes it's useful in order to learn and to understand how things work.
Is there any more questions? Oh, there's one.
Okay, thank you very much. Felipe, you mentioned about the problems which you solved, or like how much you were able to accelerate the execution of the program by introducing the life cycle. So can you give us some rough numbers? It can be from the most recent project in general. How much faster, or what errors did you handle through it, or like, can you tell a little bit more about this?
Yes, sure. So from the last project when I used the lifecycle nodes, these were used in order to handle the transitions in the navigation stack of our robot. So our robot was running two navigation stack nodes. So one for the robot itself and another one for a second robot that our main robot was controlling. And when it was not necessary, this let's call it the main robot was doing the processing of the information from both navigations, and it was getting the sensor inputs from both robots. And it was necessary to find a way of reducing the CPU usage and the load on the main computer, because we were running the navigation stack, we were running sensor processing, we were running machine learning applications, and that had quite high CPU consumption. And one way that we found to optimize the system was to simply disable the second navigation stack that was running for the secondary robot whenever it was not needed. And if we had to kill the entire application, it would take around maybe 1 minute in order for this robot to be completely ready to work again and to navigate. And using the ROS to load knife cycles, we could keep the configurations, and we just had to transition between the inactive and active state, and we were able to reduce significantly the time that it would take for the entire system to be up and running and to be able to run again. Also, another benefit of just transitioning from the inactive and active state is that you do the sensor processing, but with ROS2. ROS2 uses DDS, and you also can reduce significantly the load that you have on your network, especially if you have communication between two different computers or two different robots. You can significantly reduce the load that you have on network and bandwidth requirements. I hope that answers your questions. It's hard for me to give exact numbers, but the reduction in the load and in the bring up time was significant.
From what I remember, it was like 30 seconds up to 15 seconds, right? So twice as fast.
Yes, it was. The customer was happy with the improvements. Yeah. Anyone has questions, please?
So my question is, so if I understand well, the ROS is for controlling the robots. Can you create some simulation in terms of, can you create some environment for the robot, like for prototyping? So give some constraints to, for example, to your turtle, that if it goes out of the box, then it will go on the error processing state and so on. So that's my first question. And the follow-up question, if this is true, so if you can create an environment, is there any module in the ROS system for the reinforcement learning, so that you give some actions for your robot to assign some rewards or so to reward your robot if it goes well, and to punish them if it goes wrong.
Okay, so responding to the first question regarding transitioning between the active state and the inactive state, if you have some kind of error in your system, as far as I am concerned, the simulation that I'm using only throws an error that is something that shows on your terminal. I don't think there is any kind of diagnostics from the simulator that I'm using that is called the turtle sim. So it would not be possible for me to handle processing on this information that I got from the turtle sim, but the turtle sim node itself, it would be able to transition between the states. And for example, if the turtle hits the wall, it would be able to maybe disable the subscriber that is getting the information from the twist command in order to move the turtle. Regarding the second question, regarding having some kind of reinforcement learning in order to adapt to the movement of the turtle, I would say that that is something that is more related with the decision making of the robot and what happens in any kind of circumstances. So if for some example you are hitting the wall, or if let's use another example. Imagine that your robot, for some reason, is not the readings that you're getting from the IMU does not correspond to the readings that you're getting from your odometry. This means that your robot is sliding for some reason. It can be in a terrain that it has some kind of slope, and your robot is sliding, and you can get some kind of feedback loop in order to reduce maybe the velocity of your robot, so that you can detect the situations when the robot is sliding, and you can correct the behavior, that the way that your robot handles each one of the situations. Anyone has questions?
Anyone else? Maybe the last one question for me. Do you have any personal experience where the whole concept of lifecycle nodes were very helpful or probably not very helpful in your use case?
Yes, this is also mostly related with the question that Jan asked, when it was necessary in order to speed up the way that we are handling the entire processing of the data and reducing the CPU load, when it was not necessary that second navigation stack. That was a way that we found to improve the system and the way that the system was running when it was not necessary to have that second navigation stack. And this can have multiple impacts. For example, when your ROS system is under load, you'll have delayed messages. And if you have delayed messages, for example, from your laser scan data, or from the odometry of the robot, or from the IMU, so on and so forth, it will propagate the bad estimations for the localization of your robot. So the precision of how your robot is localized, it won't be as good. So this was one of the ways that we found in order to also improve the overall stability of the system and the robustness of the system and how everything was being handled and run in our application.
Okay, thank you very much. I'm satisfied with the answer. And thank you very much for such exhaustive presentation of the topic.
You're welcome.
Okay, so that was the last question, I suppose. Any more question? Okay.
Okay, so just thank you very much. I hope you found this presentation useful. If you want to have access to the examples that I ran here, just access the GitHub page that was displayed here, and you'll have all the information that you need. And not only just about the ROS to node life cycles, but also some basic ROS, I would say, ROS basic tutorials on how to create publisher subscribers, how to create launch files, configurations, so on and so forth. You can get some information here. And if you also want to check the additional resources from ROS, I think it's a very, very good decision, and you'll get for sure a lot of information from the ROS docs and many, many tutorials that will speed up your understanding and learning of the robot operating system and robotics in general. That's it. Thank you.
And of course, if you allow us, we can share your presentation on the social media for the audience.
Of course, yeah.
Yes, thanks. Okay, so I suppose that was the end of the official part.
Okay, thank you very much.
Thank you very much. So once again, we can do applause for Felipe. And okay, so it's the end of the official part of the the light. It's the official part of the event. So right now you can just grab a beer, networking, etc., etc. And thank you very much for your attendance here. And we suppose that the next event will be something like maybe in the end of the year, something like that, before Christmas, I suppose. So stay tuned for the more information about that. And yeah, I suppose. Oh, yeah.
So you should find more information about next events on LinkedIn. Definitely follow us there. As next event will also give you some information ahead of time, also on Facebook and on Meetup. On Meetup we can, or
Yes.
yeah, on Meetup as well. So we should announce it around like a month before the whole thing will take place. Also, we are open for presentations. If you have anything interesting to say to us, to show the community in here, feel free to reach us. Yeah, we will give you time, etc. We'll provide you with everything, as for example, Felipe. So definitely feel free to reach us. We'll be really grateful for that.
Yeah. So thank you very much, and have a nice evening.